All right, so this is part 3 of the marking period 4 review. Make sure you've got your reference table and a calculator. 101, which type of equilibrium exists in a sealed flask containing Br2 liquid and Br2 gas? So between the two, the only difference here is a phase equilibrium, so it can't be solutions. And because it's going back and forth, it must be a dynamic equilibrium. Dynamic equilibrium. Which change will not affect the equilibrium concentrations of A, B, or A2B3? If you add more A, you're going to shift away, so that's not going to do it. If you add a catalyst, it is going to speed up, so that's not it. If you increase the temperature, you're going to shift this way, so that's not it. So if you, excuse me, wait, hold on. Ooh, I forgot. Whoops. The concentrations, that's the key. If we add a catalyst, it's going to speed up the rate of the reaction, but it's not going to affect your concentration. So that is our answer. Increasing temperature would shift. And if you increase the pressure, first of all, we have gases. We have unequal numbers of moles. So we have 2 and 3. This side has 5. This side has 1. So you're going to shift from more to fewer. So that would affect your concentration. So yeah, a catalyst just gets you there faster. It's not going to change your concentrations. See, this is why I would never get 100. Ammonia is produced by the Haber reaction, the formation of ammonia. So how are we going to get more NH3? Well, we're going to need to shift to the right. How can you shift to the right? An increase in pressure, decrease of pressure, removal of N2, H2. All right, let's talk about those because those are easier. H2 and N2 are both on this side, the left side, reaction side. So if I remove that, you're going to shift to replace it. If I remove this, we're going to shift to replace it. So those are both out. So now let's talk about pressure. So if you, first of all, have gases, which we do. Do we have unequal number of moles? Yes, we do. This is a 1 and a 3, so that's 4. This is 2. So if we increase pressure, you're going to shift this way towards the NH3. So that's going to be your choice. And if you decrease pressure, it would be the other way. Which causes equilibrium to shift to the right? Adding a catalyst. Remember, we just talked about how that speeds it up. It doesn't actually change your shift. Adding more O2. If there's too much O2, we shift away. So that's our answer. Whoops. I don't know what I'm doing with that. All right, 105. What happens when H2 is increased? So H2 is on this side. Too much, so it's going to shift this way. And so since it shifts to the right, N2 is going to go down as NH3 goes up. So see? Increasing the temperature, which would be this, will cause it to shift to the left, and HI will go up. Whoops, this one. Get that out of here. 106 is A. 107, in terms of disorder and energy, systems in nature have a tendency to undergo changes in... Okay, so if you go on vacation over the summer and leave your lawn, what's it going to look like? Well, it's going to be more disordered. Hold on a second. Okay. Sorry about that. So more disorder. And so since you've been on vacation and you haven't been maintaining your lawn, how much energy have you put in? Very little or none. So greater disorder, lower energy. Based on reference table J, which reactants react spontaneously? Okay, so what this means is the first one has to be more active. And since they're all metals, we're only looking at the metals of here. Okay? So let's go to table J. Wrong one. So here's table J. And you know what? I forgot all the different questions. All right, so I'm actually going to look at it. Paper table J. You look at yours. I'm not going to put it on the screen. Is magnesium higher than zinc? It is higher. So that should be our answer. Let's just make sure. Is copper higher than iron? No, so that won't work. Is lead higher than zinc? No. And is cobalt higher than sodium? No. So the singleton has to be more active. It's a chemical name for that. So CH3, CH2, CH2, CH3. So I can see that they're all single bonds, so none of these. Meth, eth, prop, bute. If you forgot the organic reference tables, bute means 4. So butane, choice A. Number 110, saturated means single bonds. So ane, that's part of reference table Q. What is the name given to the box? So we have a 2-carbon group. So 2 carbons is eth, and we end it with a YL. That's an L, ethyl. The 2 elements in alkenes and alkynes. Well, these are organic, so we have to have carbon and hydrogen. These are called hydrocarbons. A molecule of which has a multiple covalent bond. So if you go to table Q, you'll see the multiple bonds are either CnH2n, which is double, or you double subtract 2. These are saturated single bonds. So either double them or double them and subtract 2. So if you follow this, or you could just draw them. CH4, nope. C2H4. You know what? I don't need to draw this because this is double the hydrogens as much as carbons. So there you have it. What is the name of this? So meth, eth, prop, bute, pent. And we've got a double bond, so this is ene. Triple bond would be ine. Final thing we ask ourselves is, where is it located? So we number our carbons. 1, 2, 3, 4, 5. Or is it 1, 2, 3, 4, 5? So if we label it this way, it would be after the third. If we label it this way, it's after the second. Which one's the right answer? It's the second, because we want the lowest number possible. What is this? So all we have is a hydrocarbon, so it's not an alcohol and it's not an aldehyde. So then we say, okay, we've got a triple bond. Going back here, triple bond is called an alkyne. Use your reference tables. Cyclic hydrocarbons, it's called a benzene. That's something we memorized. Looks like this. And each of those points is a carbon, alternating double bonds. We did not talk about cracking, so don't worry about that. But even if we did, cracking means you have a really long carbon chain and we break them. We crack it. So we have smaller molecules. And the smaller the molecule, the lower the boiling point. So if I did, for some reason, talk about that, it is choice C. Petroleum can be separated into different fractions by the process of fractional distillations because the fractions we are boiling this separation of liquids based on their boiling point, and the whole point is they are different so we can subtract them. Alcohol and ether have the same molecular formula, C2H6O. So talk to me about functional groups and properties. So first of all, alcohol, ethers, they're 2 different functional groups. See how they're 2 different categories? So it's got to be the different functional groups. And since they have different functional groups, their structures are different, and so they have different properties. So different. 119 is D. Isomers have the same number and type of atoms, different arrangement. And I gave up on that. So I know that A is out because the first structure only has 1 carbon, the second has 2. The second, you might think the second is the answer, but it's not, because these are just mirror images of each other. So it's got an OH group off of one of the bonds. That's not it. We've got 1, 2, 3 carbons, 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and it's got to be C. What makes D wrong? Number of carbons. So yeah, the same type and number, just different arrangement. Looking for this functional group, go back to this. C double bond to an OH is organic acid, which is, it just says acid. Don't get confused by that. Which pair is an alcohol and an acid? So again, I'm not going to flip back and forth to the reference table, but if you look here, we're looking for an alcohol. Alcohols have just an OH group, just an OH group. So this is an alcohol. And an acid is, like we just said up here, C double bonded O to an OH. So that would be B. So B and D. What is the name of this? Methethprop. Well, that doesn't help. So the functional group is C double bonded O at the end of the chain, which is an aldehyde. How do I name it? It ends with an AL. That's actually the same one that was on the reference table. Name this methethprop, C double bonded O, but it's somewhere in the middle of the chain now. So if you're in the middle of the chain, it's called a ketone. So propanone. There we go. Which is 1,1-dibromopropane. So first of all, let's break it down. Propane, methethprop is 3 carbons. So no, no. Then we have 2 bromines. Well, they both have 2 bromines. But the thing is, it says 1,1. So what that means is, what that means is both of the bromines are off the first carbon. This in choice C would be a 1,2. This is a 1,1. So choice D. There she is. Old Granny Esther's eyes. Looks creepy when you do it that way. CH3, CO, O, CH3. There she is smiling again. Hi, Granny. This is old Granny Esther. C double bonded O to an NH group. C double bonded. Okay, so here it is. It's called an amide. So amide. So the question is it going to be a 1? Oh, no amines. Is it 1 or is it 4? Well, we always want the lowest number possible. Wait, did I say amide? Hold on a second. Oh, what the heck? Sorry about that. So I looked at the wrong one. I thought there was an O there. There is not. Whoa, what is that? Ooh. I thought there was an O there. There's not. It's just NH3, so that's amine. It is amine. See, I told you I wouldn't get 100 on the Regents. So it's 1, 2, 3. It's the 1 butanamine. Sorry. Ether has a C, has an O somewhere in the center. So CH3, CHO. That would look like this. No. CH3O, CH. There it is. That's the ether bunny. Can you see it? Let's erase that monstrosity. Yeah, choice B. Take your time, go through the reference tables. What is going on here in 130? Looks like we are adding them together, breaking the multiple bond, finding extra spots. In 131, we have an organic compound and then a bromine, and then it looks like one of the bromines jumped in and one of the H's came out. So that means it is a substitution reaction. Substitution. ... That's important. That means it's going to keep on going. Super long polymer chains. What's going on here? Well, what do we got? Oh, look, there's old Granny Esther and an alcohol. Oh, no, sorry. Not, oh my gosh. I'm trying to go too fast. This is an organic acid. COOH, not COOCH. Acid and alcohol. This forms Granny Esther. Here she is. 2 O's here. How did old Granny Esther get so old? She drank alcohol and she did acid. Fermentation is the production of alcohol. So A is an alcohol, C is not, B is not, C is an alcohol, D is not. So the question is, would an alcohol have any other products? Would a fermentation have any other products? And it would. It would have the carbon dioxide, the bubbly nature of a beer. All right. produces water and carbon dioxide. So that's a combustion. This is a hydrocarbon plus oxygen yielding water and CO2. Production of a soap, the one that has soap in it. See how soap is hiding? Okay. During this reaction, each element changes in atomic number. Can't ever do that. Oxidation number. I think that's the answer. Number of protons? No. Number of neutrons? No. That would be an isotope. So it is oxidation states. When they're by themselves, they have an oxidation state of 0. When they're in a compound, we go to periodic table to find out which. So Ca is +2, O is -2. We're in redox now. What are the two oxidation states of nitrogen and NH4NO2? So we need to think of it as NH4 and NO2 like this. And this is a +1, and this is a -1. So here we have a +1 for that. And so we'd have a -3. Over here we'd have a -2, and this would be a +4. And I screwed something up, didn't I? This would be a plus, unless I can't. Oh, it's because I'm not trying to make it neutral. I'm trying to make it -1, so it would have to be a +3. Excuse me, +3. So this would give you -4. This would give you a +3. So yeah. See, I'm telling you, you can't go too fast. Which is most easily oxidized? You need to go to table. Whoops. Table J. Table J, the most easily oxidized is highest on table J. I'm not going to flip to table J on the screen. I'm just looking at it. So silver is one of the lowest one. Cobalt is higher than that. Copper is lower than cobalt. Magnesium is the highest. Most easily oxidized is highest on the table. Which is a reduction half reaction. Leo the lion says grr. Gain of electrons is reduction. When you are gaining electrons, your charge goes down. The charge is reduced. So in part A, I have Fe alone, 0, becoming Fe +3. That is a loss of electrons. In B, I have a gain of electrons on this side that, no, this doesn't match up. In C, that also doesn't match up. So in D, I have +3 gaining. See how they're on the reactant side? And then it becomes 0. So it is choice D. During an oxidation-reduction reaction, the number of electrons gained has to be equal to the number of electrons lost. Has to be equal. Oxidation. Leo the lion says grr. Loss of electrons is oxidation. So if you go up here, anybody by themselves is 0. So it looks like zinc went from 0 to a +2. That is a loss of electrons. So we're talking about zinc, which shows losing electrons. It would be part B, because electrons are being spit out and the charge goes up, which is a reduction half reaction. Gain of electrons is reduction. So who's gaining? And when you gain electron, your charge goes down. So the copper is gaining electrons, and so we are at a +2, and now we're going to a 0, so it's D. Okay, so this is a 0, and this is a 0. So how are electrons transferred? They're transferred from the copper to the Ag+. Okay. Which will spontaneous react with zinc, but not with Mg? So this means it's somewhere between magnesium and zinc. Magnesium has to be on top because it won't react. So manganese is in between those. So that's probably it. Yeah. I don't need to go through the rest. Conservation of charge means the charge is the same on both sides. So in A, this is overall -1. This is overall +1, so that's not it. This is +2, -2, so that means 0. And this is also 0. That's our answer. When an equation is correctly balanced, it must show conservation of charge but not mass, mass but not charge, both charge and mass. All right, now we need to balance this. So here we go. So oxidation half reaction. Who lost? Magnesium did. So 3Mg becomes 3Mg +2. So mass is good, but charge is not. So we have an overall plus 6, so we've lost 6 electrons. And the reduction is Fe plus 3 becomes Fe 0, and we have 3E minus, but that's not balanced, so then we'd have everything multiplied by 2 in order to balance. So it's 6. So the Fe plus 3 and Fe have a coefficient of 2 because a total of 6 electrons is transferred. Yes, choice B. That took a minute, but we got there. When comparing voltaic to electrolytic, oxidation, the fat, red, cat, ate an anorexic ox. So oxidation happens at the anode in both. Other things are different, but fat, red, cat, ate anorexic ox always occurs. What form of energy is converted to electrical in a voltaic cell? So it comes from the chemical reaction. Okay, folks, I'm going to take a break here. Check back with me if you've got any questions, and for part 4. Bye.